there is a moment. If you have ever sat over the wing on a long flight, when you look out the window during turbulence and watch the wingtip move. Not a little. A lot. It swings upward, then rebounds like a slow, massive hand waving goodbye to the ground. And something inside you tightens because that looks wrong. That looks like something about to snap. So here is the question nobody asks out loud because they are too busy gripping the armrest. Why would the people who built this machine let that happen on purpose? Most people, if pressed, would say the wings flex a little to absorb shocks, the same way a car's suspension compresses over a bump. That logic feels solid. You have a rigid structure. You add a bit of give, and the give protects the passengers from the worst jolts. It sounds like a safety feature. It sounds like smart engineering. The problem is that explanation describes a shock absorber, and a wing is not a shock absorber. That mental model is not just incomplete, it has the causality completely backwards. Here is the fact that stops people mid-sentence when they hear it for the first time. The wingtips of a Boeing 777 can flex upward by almost 4 meters, which is roughly the height of a stack of 13 carry-on suitcases balanced one on top of another. During the most extreme certified stress tests, the wings are loaded until they bend upward by more than 7 meters. A fully loaded 777 weighs close to 300,000 kilograms, and its wings are designed to bend like enormous fishing rods under that load, with the fuselage as the handle and the sky as the line. Then this is what nobody tells you when you book a window seat. The bending is not a side effect of the wing doing its job. The bending is the wing doing its job. Here is how that actually works. A wing generates lift by creating a pressure difference, lower pressure above the wing, higher pressure below. That pressure difference pushes upward, and that upward push is what holds the plane in the sky. But that same upward force is distributed all along the wing, from the root where it meets the fuselage all the way out to the tip. The wing is essentially being pushed up from below along its entire length, while its center is held in place by the fuselage. That is the textbook definition of a bending load. A wing that could not bend under that load would instead accumulate enormous internal stress at every point along its structure. There's stress that would have nowhere to go except into the material itself, weakening it, and eventually fracturing it. Flexibility is not a concession to real-world imperfection. Flexibility is the mechanism by which the wing distributes and releases stress continuously, the same way a tall tree survives a windstorm not by being rigid, but by swaying. A completely rigid wing, under real flight loads, would be a wing that is quietly destroying itself from the inside every single minute it is in the air. The reason engineers understand this so precisely goes back to a catastrophe that shook the entire industry to its foundations. In 1954, the de Havilland Comet, the world's first commercial jet airliner, began breaking apart in mid-air. It was the most advanced passenger aircraft ever built, and it was killing people at cruising altitude for reasons nobody could explain. The investigation that followed was one of the most rigorous in aviation history, and what engineers discovered was a phenomenon called metal fatigue. The square windows on the Comet created stress concentration points where the fuselage skin was being cyclically flexed and released with every pressurization cycle, thousands of times across the aircraft's life. The material was not failing under a single overload. It was accumulating microscopic damage over time, invisible to inspection, until it suddenly and catastrophically gave way. That investigation changed everything. Engineers stopped thinking of aircraft structures as things that either break or do not break. They started thinking of them as things that accumulate damage over time, and they redesigned every load-bearing structure accordingly. Wings that flex are wings that redistribute stress rather than concentrate it. The Comet's legacy is that every aircraft you have ever boarded was designed around the lesson that rigidity is not strength. The ability to yield, gracefully and predictably, is what strength actually looks like at scale. And once you see it here, you start seeing the same principle everywhere you look. A fishing rod bends dramatically when a fish runs because a rigid pole would either break or tear the hook free. The strings on a guitar are not bolted taut between two fixed points, but held under tension that the whole body of the instrument absorbs and redistributes as it vibrates. The tall skyscrapers in earthquake zones are built to sway laterally by a meter or more, because a perfectly rigid building would transfer all seismic energy directly into its connections, which would then shatter. A longbow works because the limbs flex and store energy in the wood itself, then release it as the arrow leaves. Suspension bridges hang in elegant curves rather than stretching in straight lines, because the curve is the structure's way of converting tension into something the cables and towers can manage without snapping. Even the bones in your forearm bend slightly when you catch a heavy object, invisibly and instantly, before they return to shape. The world is full of things that survive by bending, and you almost certainly never noticed any of them. The honest limitation to all of this is that flexibility has a ceiling. And that ceiling is very carefully defined. Engineers design wings to operate well within their elastic range, meaning the metal returns to its original shape after each flex. But every flex cycle is also a tiny deposit into a fatigue account, and that account has a maximum balance. Every commercial aircraft has a design life measured not in years, but in pressurization cycles and flight hours, because engineers know that somewhere beyond that boundary, the material's ability to recover is not guaranteed. When airlines talk about retiring aging aircraft, they are not being sentimental. They are enforcing the arithmetic of metal fatigue. The wing that saves the plane by bending is also the wing that, over a long enough timeline, bends its way toward its own limit. And if you think the physics of airplane wings is fascinating, wait until you find out why the engines are mounted in front of the wing instead of behind it.